Today is June 14th, and we're going to go on with chapter H, okay? And there are some very particular characteristics of the way we treat this problem in naval engineering. Okay, so we're going to start in that direction. At the end, I would like to spend some minutes in order to say something about the calculations that I'm expecting in your report, okay? Because you measure strain and also acceleration. And I don't know. Let's see how, okay? So I'm going to say something about that, okay? So you all have the class notes, so this is just a quick sum of explanation. Giovanna, can you see my full screen?
Yes, Doctor.
Okay, so this is chapter 3, and this is the full content of this chapter. So we're going to start today by the equations, which are very similar to the exercise number 1 in the evaluation. Okay. Then we will go to, you see, hydrodynamic force is proportional to acceleration. What do we mean by this, Ms. Astudillo? Hydrodynamic forces proportional to acceleration. What terms come to your mind when you listen to this?
The dynamic force.
Proportional to acceleration. What comes to your mind immediately? Ms. Drogo, what comes to your mind?
That the dynamic force is applied in the center of gravity of the body and
Galarza?
It's pressure or resistance.
Oh? Immediately, Sayo. Proportional to acceleration. This is in
Newton, second law.
no. What's the force that we study in chapter 2? What's the concept that we developed in chapter 2? We integrated the pressure to get the force, and we introduced the concept of Delgado. The concept of added mass. Come on, people, added mass. Added mass times acceleration gives you the force, okay? So that's that. And in chapter 3, I'm sorry, subchapter 3.3, we're going to study similar, but in this case, it's potential. So we are not going to include any viscous effects, because in this case, in this problem, the potential flow is good enough to estimate these forces. Okay, so we have here the restoring; those are the static in 3.1, in 3.2 and 3.3, hydrodynamic in 3.4, excitation. This is from the waves. And finally, after we have everything in 3.5, we can calculate the response. Okay, so you will see this is like a 2D problem that we have studied. And the problem is that all the matrix is full. So we have, it's a 2x2, but complex, because damping is there and we cannot avoid it. And finally, the end, Engineer Isaac, we will invite him, so he will describe how can we use MaxSurf in order to start our calculations. Okay, so that's the idea behind this last subchapter. So this is the agenda for this full chapter. Okay, so let's start. This is something that you have heard me before, but hopefully after this, you will keep this in your memory. Okay, when you study ship dynamics in general, especially in the US context, okay, in the American context, what do we mean by this? Okay, in general, dynamics means dependence on time, right? So could mean this, okay? Could mean vibration. And we talk about vibration, that means that something deforms. Okay, so the restoring action, when you talk about vibrations, are the internal forces in the structure which tries to bring the structure back to the static equilibrium in general. Okay, and you saw that last Friday, not in the Coliseum, but at the lab. And you see that the structure deformed on one side and then came back up, then went to the other side, and the internal forces brought the structure back to the upward position. So it's deforming, and you measure the strain. That's because it's some deformation of the structure. Now here, we can recognize the vibration of the whole ship. For example, here, figure, I'm showing you the torsional vibration. Okay, so you see that this is coming in this direction, while the aft region of the ship is moving in the other direction. So it's like something like this. And if there is some excitation, for example, from the propeller or from the main engine, which has huge main engines, at similar frequency, you could have resonances and all of that. But also we could have local vibration. Now, for example, the vibration of the superstructure here, okay, can vibrate up, forward, and upward. And also the propulsion shafting. It's typical. Could be torsional, lateral, longitudinal. But in all of these cases, there is some deformation. And usually frequencies are medium or high in general, okay? Very, very, very large ships, okay? In those cases, these natural frequencies are low. But in general, we expect them to be not that small, not that low, okay? So that's the first thing that we can understand if we say ship dynamics in general, okay? The other meaning is that we mean the response of a ship in waves, okay? In this case, we assume that the ship is rigid. See, in the first case, deforms. In the second, it's rigid. That means that it doesn't deform. So you can have 6 degrees of freedom, and the excitation in this case are the waves. Okay, in general, waves are phenomena with low frequency. So in general, instead of omega, since omega is very low, we express the frequency as the inverse of the period. So instead of this, we say the period is 1/f. So usually, when we talk about this phenomena, we describe with the period, not with the frequency, because the frequency is so low. Okay, so you can see here, it's a huge ship in a huge wave. So you see that there's some water coming above the ship. And finally, the other application in ship dynamics is this area, maneuverability. Okay, now in this case, there is no restoring effect. That means that, for example, you take the ship and move it on the side. There's no net force which brings it back. Okay. Similarly, you make it rotate, like in this case, the ship is rotating. Okay, and it doesn't since there is no restoring effect, there is nothing which tries to bring the ship back to its original position. And that means that if there is no restoring effect, there is no free oscillation. Okay, no oscillation. What do they do? Well, they do problems like this, for example, okay? So they're coming in this direction and they try to make this maneuver, and they try to determine how much is this. This is a tactical diameter. Okay, if this is very large, that means that the ship doesn't have enough maneuverability. And for example, when every time we have an accident around the Galapagos, they make a question, they put a question mark on the capacity of maneuverability of the ship. Because if they don't have enough, I mean, they cannot handle around all of these obstacles and some accidents could happen, okay? Another thing which is another problem which is very interesting is the direction instability, okay? From time to time, you can listen that you have a ship, it's moving forward and the rudder is in 0 degrees, and suddenly the ship starts changing course, changing the direction of the course. But the rudder is it's in the center, and there's no currents, no wind. Yeah, but it's unstable, right? So it's I mean, it's a problem that it's interesting to analyze. Okay, so that's the type of problems that they deal with in maneuverability. So in general, this is what we mean. Okay, and of course, you can recognize that this is what we are going to study in ship dynamics. Okay, so the course on ship dynamics, Dinámica del buque, is to study the response of the ship in waves. Well, we have to be careful because with ship dynamics in general, in some cases, we can mean the vibration or the maneuverability problems. Okay, so this is the area where we are going to be working in the next 4 chapters. Okay, so here we are, motion of shipping waves. So the body that we are going to analyze is a rigid body. Okay, so since it is a rigid body in general, we can have 6 motions, okay, in general. Your responsibility to put these names in your memory, these terms in your memory, okay? So we have 3 linear and 3 rotations. Now, this is the system of reference system that we're going to use. This is the X, okay, pointing forward to the ship. This is the Y direction. Is this port or starboard, Miss Lopez? This is port or starboard, Miss Lopez?
Starboard. Starboard.
Do you agree, Mr. Iñiguez? Is this? Zambrano, what do you say? Is this port or starboard?
That's board.
That's port. Yes, that's port. So, yeah, you are looking from above. This is your ship. Okay. That's X. C is upward. Okay. You see, this is Y. So this is port. So you have to be careful because if you specify a positive rotation with respect to the y-axis, positive rotation, that means that the forward end enters into the water, okay? We have to be careful because every author in every computer program can use a different reference system, okay? Some people don't like under a pitch rotation, the forward end to come inside the water. So what they do is they define the Z positive pointing downward, okay? And in that case, the Y will point toward starboard. And in that case, rotation in pitch, positive rotation in pitch, will bring the forward end up. But the problem is that you have the Z positive downwards. So the only recommendation is be careful. That's all, okay? Before you start using a program, start by there. Okay, what's your reference system? Okay, so to avoid problems with the phase shift. Now, so we have translation in X, we call it surge, translation in Y, sway, vertical translation, heave. Rotations with respect to the X-axis is roll or balance. Roll is I think it's usually that's the way we call it. Rotations with respect to the Y-axis is pitch. And finally, rotation with respect to the vertical axis is yaw, okay? You are responsible for keeping all of these 6 terms in your memory, okay? Now, since it is a 6 degrees of freedom system, okay? Can you imagine? You're gonna have a 6 by 6 equation here, okay? And here we have zeta 1 until zeta 6. See, this is the dynamic matrix. Can you imagine calculating natural frequencies and things like that in this case? It's very complex, okay? So that's why usually what we do is we separate it in what we call 2 planes, okay? One is the vertical plane. So in the vertical plane, we have the combination of heave and pitch. They are coupled, okay? So if you study the motion of the ship in the vertical plane, you cannot study heave unless you include pitch and vice versa. Okay, now, there are simple cases where this coupling disappears, okay? For example, in our course, in some examples, we could consider, for example, a box barge, right? A box barge floating with no trim. In those cases, yes, you could have the 2 motions uncoupled, but in general, it's basically impossible to avoid it. So you cannot study heave without pitch and vice versa. Okay, now, heave in general, we're gonna call, this is the 3rd degree of freedom, so we call it eta 3, okay? So eta 3 is in general, the function, and it depends only on time because we consider this as a rigid body. In pitch, we call it eta 5 because it's the rotation with respect to the Y-axis. And the other plane, or the other combination of motions is the lateral plane. And in this case, we consider a sway, roll, and yaw combined. Now, this is what we're going to study in chapter 3. And we're going to study uncoupled roll in chapter 4. We are not going to study the 3 motions coupled. Okay, now, in general, when you study a motion uncoupled, you can expect in general the amplitudes to be larger than in the case of coupled. Why? Because it's like think in terms of energy, okay? The excitation puts some energy in the system, and the system responds with motion, velocity, and goes up, increasing the potential energy and things like that, right? If you have uncoupled, all the energy has to be shown in one direction only, okay? So in general, all the energy goes to one motion, so you can expect the amplitude of that motion to be large. When you receive this energy and you split it, yeah, okay, into several options, several motions. In general, you can expect the amplitude of each one of them to be smaller than in the case of uncoupled. So when we study the roll, uncoupled roll, you could consider that as a pessimistic situation, okay? And it's quite common, especially in the last regulations from the IMO. The last group of regulations, they are completely dynamic, which is something more realistic, okay? So we're going to start by working in the Heave+Pitch couple, and this is chapter 3. And that's what we call this in the vertical plane, okay? So we're going to start by deducing the equations of motion, and then we're going to spend some time explaining how to calculate each one of the terms in the equations of motion, and at the end, we're going to solve it. So this is general, the situation that we're going to be, or the reference system that we're going to be using, okay? The origin of the reference system is here, okay? It's not in G, it's in the midship section, okay? Y points forward, Z points upward, and Y points to the port side, okay? So rotation with respect to the Y-axis means that the forward end goes down. As I said before, there's something that people don't like. You have a differential force acting on the ship, and that will generate, of course, a vertical acceleration. Now, if you consider moments, okay, and this is positive moment with in the positive X position, this will generate a negative rotation, okay? So we have to be careful with the signs here, okay? Now, why do we put the origin of the system here and not on G? The problem is this, okay? To calculate all of this, we need the ship lines, okay? And usually, when you remember from naval architecture, okay, what we do is we have sections, right? Remember here, I have section 0, and here I have section 10, usually, right? Now, in every condition, the position of G is going to change, right? Right. So if you have the origin here, then means the station 10 moves. So I would have to prepare a different lines plan for every loading condition. That's just too much work. So people said, okay, we're going to keep the origin here, and we simply consider that the loading condition will change G, the position of the centroid, and that's it. Okay, now you also see that from here until G, there is some distance, okay, in X, and also there's some small distance in Z, okay? We're going to simplify that in a minute, okay? But in general, we expect the ZG to be very small, okay? The ZG would be the vertical distance from the flotation line until the centroid. That's usually very small, okay? In general, okay, if you have a situation and you want to know more or less what is the kg, if you have nothing to estimate it, you simply take the kg equal to the draft. That's a very simple estimation. So that means that the ZG is basically 0. So in general, we expect this value to be small, and that will simplify that. Okay, now here, there's something which is very important is that we have a 2 reference system, okay? We have a fixed reference system here, okay? This is fixed. And we have another reference system. This is small x, y, and z, which is moving with the ship. Okay, and this reference system has, since it is moving with velocity u, is an inertial reference system. Okay, you recall from dynamics. Okay. Right, of the ship in the plane, in the vertical plane, are these: eta 3, and this is, as we said before, is the vertical displacement of the midship section. And eta 5 is the rotation with respect to this axis. Okay, so if you apply the rule, right-hand rule, okay, your thumb points in the z direction, and so the rotation, the positive rotation in the y direction is like this. So this is a positive eta 5. And of course, this is a positive eta 3. Okay? We have to be careful with that. Let's do a break here. You can review quickly your class notes. And when we return, we're going to deduce some relations for the mass times acceleration, inertia times acceleration for this case, okay? So let's take a 5-minute break here and